Okay, good morning. So we are in third module here, and we had solved some problems related to shear force and bending moment. Okay, so now we'll look into the plotting of shear force and bending moment. Okay, so this was one problem which we have solved over here. Okay, a cantilever beam, uh, and we have obtained the values of shear force as well as bending moment. Okay, so these are the shear force values what we have here. At D it was 0, C 40 and 50. Before I crossed point C it was 40. Once I crossed this concentrated load it increased to 50, and same at B. When I was just right side of that concentrated load at B, the shear force value is 70. When I cross this concentrated load it will increase to 100 kilonewton. At A it is 140, which is equal to this vertical reaction at A. Okay, same we have considered the bending moment here. So bending moment, when we adopt the sign convention, it is coming out to be negative. Now when I start with point D, okay, so here I have a couple which is applied in clockwise direction, 40 kilonewton meter. So this is the section, and right side of the section, if the moment is acting in clockwise direction, I'll be taking negative sign for that. So for that purpose, minus 40. And when I move to point C, the value of bending moment is minus 80. Minus 40, due to this UDL, it is coming out to be 20 into length of UDL into 2 by 2, half the length. Okay, it will be acting at the center of this length. So moment will be that total load multiplied by the distance. Total load is 20 into 2 into this 2 by 2. So minus 80. And when I come to point B, it is minus 140, and at A it is minus 380. Okay, which will be equal to this MA reaction at A. Okay, MA. Now we'll take up the plotting part. Okay, we have seen some this one plotting of bending moment and shear force, and we'll continue with this problem for plotting the bending moment and shear force. So first is I'll be taking the beam. I'll be representing it with the straight line. Okay, so this is the beam what we have. Okay, so this line will represent the beam, and on this we have to plot those shear force and bending moment over here. Okay, so okay, now for that purpose what I'll do is I'll first take the plotting of shear force diagram. So I can start with D. Shear force here it is 0. So at C, when I come to point C, so what was happening to the shear force? The value of shear force at point C, I have it as 40 and 50. Okay, so since UDL is present on this beam, the shear force will increase linearly. Okay, when I increase the distance, the value of shear force will also start increasing. Okay, because to obtain the shear force value, what we are doing is we are taking total force to the right side of this section over here. Okay, so when I cover a distance of 2 meter, the shear force value will be 2 into this UDL of 20 kilonewton per meter, 2 into 20, 40 kilonewton per meter. So with increasing distance, the value of force, whether it is to the right side of section or left side of section, will increase when you have UDL present on the beam. So it will be increasing linearly. So considering that linear variation, okay, so what I have here is at point C. This is my point C. Note that all the shear force values are positive here, B, C, and D. So this is the B. So at D it is 0, So at C, what is happening? 40. Once you cross that concentrated load, it will go to how much? 50 kilonewton meter. Sorry, 50 kilonewton, just 50 kilonewton. Okay. So this is the variation what we have. So it will be a straight line variation. So from here to here, it will be increasing linearly. And what will happen at this point C, once you cross this concentrated load, at point C itself, there will be sudden increase in the shear force value from 40 kilonewton to 50 kilonewton. Okay. Now when you go to point B, okay, when I come at point B, what is happening? 70 and 100. I have two values over here, 70 and 100. Okay, 70 here, and to the left side, when you cross this concentrated load, it will be increased to 100. Okay, so that has to be plotted here. So we'll plot them as ordinates. Okay, so from this, it is again increasing linearly. From 50, it has increased to 70 linearly. In this portion, you have the UDL over here. Okay, so it will be varying linearly 70, and this is 100. Okay, so these are the values at point D. So how is this variation? So it is again increasing linearly. Connect them by straight line. So here at one single point, you have a sudden increase in the shear force value. Okay. And when I come to point A, value of shear force is 140 kilonewtons. So at point A, what I'll do, I'll mark a ordinate with 140 kilonewton, the shear force value. Okay. And in this region also, because you have UDL applied over here, it will increase linearly. Okay, so here also what I'll do, this will be varying linearly, linear variation in the shear force. Okay, and over here, once you cross this support, okay, so again it will come back to 0. Okay, so it will be like this. This is the variation of shear force. Okay, so entirely shear force diagram is positive because all values of shear force are positive. So this is the shear force diagram. So sir, good morning. So shear force diagram, in short, we call that as SFD. Okay, so this is the variation what we have. Now along with this, when I give the values, what I have here, it is 40 kilonewtons, 50 kilonewton, 70 kilonewton, 100 kilonewton, and it is 140 kilonewton. So these are the values of our shear force. Okay. And with that, the bending moment diagram. Okay. To plot the bending moment diagram. So here we will be plotting the variation of bending moment on the beam. So for that, I'll be taking that beam again. Okay. So the line here, this is representing the beam. And these are our points A. This is my point B, C, and D, as it is. Whatever is given to us as a beam, that will be plotted over here. Okay. And now we have to start with the plotting of bending moment diagram. For that, I require these values of bending moment. At point D, it is minus 40 kilonewton meter. Okay, we have done this calculation. So at point D, minus 40, point C, minus 80, B, it is minus 140, and at A, minus 380. Okay, now any point on the beam, okay, if so if you take any point on this beam, Okay, so I'll just roughly draw this beam over here. So you have the UDL on this beam, okay, and also there are some concentrated loads, okay, and the couple which is applied here. So when I take a section, we are moving from right to left. Okay, I told in cantilever beams it is better to move from free end to fixed end, right? So you have this intensity, load intensity W. Okay, so at any point or at any distance, when I calculate the bending moment, okay, if I just show you the equation of bending moment here, it will be expressed as, say, in this portion only between C and D, W into X by 2, like we did it at point C. It is what we did was here, see, when I came to point C, it was minus 40, this couple, minus 20 into 2 into 2 by 2, W into X by 2, okay? So that is what the equation it will be coming out to be. Or this is a quadratic equation if you observe, of second order, x to the power 2, or W x square by 2. This is what the bending moment equation is consisting over here. Yeah, yeah, and additionally, if you have couple, you will be adding that couple also here. But the whole equation, what it comes out, it will be quadratic in nature. Okay. So what will be the variation here? It will be parabolic. It will be varying parabolically. Okay. So the line representing the variation of bending moment will not be a straight line here. Okay. So it will be a curved line, okay, because power x to the power 2 is there, okay. So we'll be representing that with the curved line here. In case of shear force, what will be the variation? It will be linear because it will be just 20 into x. Okay, so I hope you got that, how the variation will be for bending moment W x square by 2. Note that when you have UDL, the bending moment, okay, diagram, when you draw it, so represent it by a curved line, a parabolic line. So first is I'll take these coordinates. What I have coordinates minus 40, minus 80, minus 140, minus 380. So all are negative, and they will be plotted below this line. Okay, below this beam line. So here it is minus 40. At point D, it is minus 40. So I'll just show a line over here. And when I come to point C, what is happening? It is minus 80 and minus 140 and minus 380. Okay, so these will be just straight lines, these ordinates what we have. So this is the ordinate representing moment at point D. Okay, and same when I come to point C, the minimum value here is minus 80. So for that, I'll just show this one ordinate, and at point B, what we have minus 140, and at point A, 380, minus 380. So these are the ordinates what I have over here for bending moment. Okay. So with these ordinates, now I have to plot the variation of bending moment. So how will be the variation? So it will be parabolic. Okay, like this. Connect these ordinates. Sorry, I'm not getting correct curve over here, but it should be a curved line, not a straight line. Okay, so you should connect that with a curved line. You have to take a continuous line. Okay, so this is our variation in the bending moment.
Right, sir.
Come on, sir. Okay, right? So it will be like this, a curved line. So what we have is the values. This is 380 kilonewton meter, and here it is 140 kilonewton meter and 80 kilonewton meter, and this was 40 kilonewton meter. And what we have is all these are negative, or the entire beam is in hogging bending. Okay, nature of bending is hogging, so entire bending moment is negative. Okay, so this is the bending moment diagram, shear force diagram and bending moment diagram. And we represent or call it as BMD. Okay, so this plotting is also important. After we calculate them, we have to plot these values of bending moment like this, and even the shear force. Yes, if you have any difficulty in this, you can clear your doubts. You can ask your doubts. Need variation. I told you the variation here. It was say in this portion, any point at any point over here. The equation what it was coming out to be is, say, between C and D, minus 40 minus 20 into, if you want anywhere between, I have calculated at a distance of 2 meter. Okay, directly at point C. In between, how will be the variation? If you say you consider any section at a distance of 1 meter, it will be given by 1 into 1 by 2. Okay, this is interval. Okay, if you take an interval x meters, then it will be x into x by 2, or for this beam it will be minus 20 into x square by 2 between C and D, the variation of bending moment. So anywhere you take it, when UDL is present, you will get the bending moment equation in the form of quadratic equation, x to the power 2. Okay, and the shear force will be a linear equation, 20 into x. Okay, so anywhere you want here between C and D, 20 into the distance. Okay, so the variation of shear force is linear here. Okay, only when we are across the concentrated loads, there is sudden change in the shear force. Okay, at those points. So other than that, where UDL was present, so in those portions the variation is linear. It is increasing uniformly. Okay, in some cases we are seeing that shear force are remaining constant also. So you have to understand that how the line has to be taken for representing bending moment and shear force. Whether we should choose a linear variation, curved line when it is a case of parabolic variation like that. Okay. In short, what I can say here, mm, say here, if you write load, okay, what type of load is present on the beam, okay, and how the shear force and bending moment varies. Okay, say in case of concentrated load, so this will be constant. Okay, it will be constant. It will be varying from one point to another point. Between the points, it will be remaining constant. This will be linear. Okay, it varies as a straight line, linear variation. Second type of load, what we can have is UDL, uniformly distributed load. So in this case, this will be linear. Shear force variation will be linear. This will be quadratic. Okay, and you may have UVL also. uniformly varying load over the beam. This will be quadratic and this will be cubic. Cubic in the sense will represent them by a curved line. That's all. Okay, indicating the variation. And one more thing is here a couple. We may have a couple. When it is a case of couple, will be sudden changes in the bending moment. Shear force will remain unaffected because of couple. Okay, but bending moment will be changing suddenly when you cross that couple. So that is gone. Okay, I'll give you that one. So in this plot, what we plotted was for the previous for that cantilever beam what we have solved. Okay. Now let's try to plot it for one more beam over here. So first is we'll go for calculating the shear force and bending moment in this beam. Here we have a overhang portion. Okay. In this case, there's a overhanging portion which is projecting outside the support over here. So this part we call it as overhang. Okay. So that is what we have over here. Now in this case also, when you go for calculation of bending moment and shear force, I require the support reactions, okay, because they are required when we start the calculation of shear force and bending moment. Okay. So here first is the reactions. Okay. So what is the reaction at the support? So here we'll come across these vertical reactions. Okay. So what are these reactions? If I take it as this as VB, this is my point B, and this is VT point. Okay, so what will be reaction over here? If I take moment about D, okay, summation of all moments about D, or first is summation Fy is equal to 0. Okay, so what are the vertical forces over here? I'll start with this end A minus 70 downward force, okay, minus 70 kilonewton, and VB plus VB, which is upwards, or which we have taken it to be upwards. Okay, and we have this UDL spread for a length of 7 meter, 4 plus 3, of 10 kilonewton per meter intensity. So since it will be acting downwards, minus 10 into 7 meters total length of the UDL, that will be downward force. And I have one more force here, 40 kilonewton concentrated load applied at C, and minus 40. Okay, and when I come to point D, I have the reaction at D plus VD is equal to 0. Okay, so summation of all the forces in vertical direction, I have equated them to 0. Or what it gives me is VB plus VD. So this will be minus 70, minus 70. This will also come out to be 70, minus 140, and minus 40, minus 180. Okay, minus 180 is equal to 0, or we can say that VB plus VD, okay, is equal to 180 kilonewtons. Okay, this is one equation. Now I'll consider moment about point D. Okay, I'll consider moment of all forces about point D and equate them to 0 to satisfy one more condition of equilibrium, which is summation of moments is equal to 0. Okay, and we'll consider about point D over here. So when I take about point D, okay, all clockwise movement, I'll take them to be positive, anti-clockwise movement, I'll take them to be negative. Okay. Here, the sign convention for bending moment and shear force will not come in picture. Okay. We are taking moment about 1 point and we are equating them to 0. Okay. So for reference purpose, clockwise will take them to be positive moments, anti-clockwise movement will be considered as negative moments. Okay. So about point D, when I consider here, there is a clockwise movement of 100 kilonewton meter. Okay, couple. So this is 100 kilonewton meter. This one, because of this one. Okay, and because of 70, what will be the moment about point D? This 70 kilonewton force will have a anti-clockwise movement about point D. Okay, so here the 70 kilonewton force is applied. I'm taking moment of that 70 kilonewton force, which is applied at this end A. Okay, 70 kilonewton. What is the distance? 2 meters here. Okay, and this is 4 and 3, 7 meter. Okay, total distance is 2 plus 4, 6 plus 3, 9 meters. What is the direction of movement? It is having a anti-clockwise movement about point D, about this point. Okay, so what is the value? Minus, because it is anti-clockwise, 70 into 9 meter. Total distance is 9 meter. 70 multiplied by this 9 meter, anti-clockwise direction. Okay, so that is the moment what we have because of that 70 kilometer. Then other than that, what load we are coming across here is we have this reaction. Because of the reaction at B, what moment it will have about point D? It will be having a clockwise movement first of all. So this will produce a clockwise movement about point D plus VB into distance is 4 plus 3, 7 meters. 7 meter. Okay. And coming to this UDL, what is applied over here of intensity 10 kilonewton per meter. So it will be having anti-clockwise. It is a downward force, and about point D, it will produce an anti-clockwise movement over here. Okay. So minus 10 into, it is present for a length of 7 meters, 10 into 7 into 7 by 2. Okay, so this is the moment due to this UDL, right? And there is one more couple at C, what we are coming across. It is clockwise couple. So plus 150 kilonewton meter, this clockwise couple I had added to my movements. Then what we have at C itself, there is a 40 kilonewton force. That 40 kilonewton force will have an anti-clockwise movement about D minus 40 into 3 meters. Okay, so this will be equal to 0. That has to come to 0. So what will be this? So this will tell me what will be the reaction at B, PB. So how much it comes? 100. Okay, minus this. Calculate this one. How much it will be?
minus 530.
Minus
530.
530. Minus 530. Okay, please see. Minus 530. You are telling me only the value of these numbers what are added.
Yes, 100 minus
Okay,
70 into 9, that numbers only.
okay, wait, minus 530. So what I should be writing here is VB into 7 minus 530 is equal to 0, right? Or what will be VB equal to in that case? 530 by 7. What VB comes out to be?
75.7.
75.7. So this is 75.7 kilo newtons. Okay, and if I substitute this value in that earlier equation, I'll come to know what is VD. Okay, so how much will be that VD? Then it will be 180 minus 75.7. So VD will be equal to how much? 180 minus 75.7. What is that? 180 minus 75.7.
104.3.
104.3 kilo Newton. Okay, so this is the value what we have. Right now, once we have the reactions, okay, now we'll go for calculating the shear force first. Okay, so what is the, we'll start moving from A to D, from left to right. When it is overhang beam or simply supported beam, I'll be moving from left to right in this direction. Okay, when you have cantilever beams, it is always better to move from free end to fixed end, free end to fixed end. Okay, so it may be like this. So here is the fixed end. So in this case, I'll be moving from right to left. If at all, if the beam is given to me in this way, okay, so we have the fixed end over here. I'll be moving in this direction. So I'll be taking a section here, and then I'll be taking the forces to the left of section. Here, if this is the section, I'll be taking the considering the forces to the right of section. Okay, so that is the difference what we will be following over here, just to keep the solution simple. Okay, so in this case, if I take point A, so what I have is shear force, okay, at A, right? So I can say that over here minus 70. I know that when before crossing this 70 kilonewton load, it is zero. There are no forces to the right side of the section, and these couples will not come in picture when we are calculating the shear force. Okay, so I can write once I cross this point A, okay, over here where concentrated load of 70 kilonewton is applied. So left side downward force, for me it is the negative sign convention, minus 70 kilonewtons. Okay, now I'll directly come to point B. Okay, shear force at B. Okay, what we have is minus 70. Up to this point, it will be minus 70. Once I cross this support over here, it will be minus 70 plus 75.57. So what I can write, it will be minus 70 plus 75.7. Okay, which comes out as 5.7 kilo newtons. Okay, 5.7 kilo newton. Okay, now it should be clear to you that this concentrated load will be increasing or decreasing the shear force suddenly. At one point itself, there will be a sudden change in the concentrated load. Okay, sorry, the shear force value. We'll take care of that when we are plotting it. Okay, so I am not no longer taking that left right of the concentrated load. Okay, so you should now be familiar with that one. Now what I have after this, I'll go to point C directly. Okay, so shear force. There is no interval which has been asked to us. Okay, so I have not taken any interval given over here. At points what are represented on the beam, at those point itself, I am calculating the shear force. Okay, shear force at C. Okay, so what I'll do, so just do this before I cross this concentrated load. Okay, I'll calculate the shear force because now UDL is coming in picture. So there will be a gradual change in the shear force value. So let me just calculate before this concentrated load, because here there was no loading between A and B. Okay, only when I cross this point B, there will be a sudden change in the shear force value. Okay, so I have calculated only after crossing point B. Before I cross point B, it will be same, minus 70 kilonewton only. Okay, now here what is happening? There is a loading which is present between B and C. So due to that, there will be a variation of shear force before, even before I cross this concentrated load. Okay, So what I have, uh, so first is here I'll take to left of B, sorry, left of C, point C. So what is the shear force? It is, we have 70. I'll take algebraic sum of all the forces to the left side of section, minus 70, plus this VB is there, which is 75.7 plus 75.7, and UDL is present for a length of 4 meter. So minus what? 10 into 4 meter. 10 into 4 meter here. UDL left side downward force. So for that, these two are considered negative, whereas reaction is on the left side of the section, but in upward direction. So it is taken positive. So this will come out to be, this is minus 40 plus 5.7. How much it will be? Minus 40 plus 5.7.
Minus 34.3.
Minus 34.3 kilo newtons. Okay, so to right side, why I'm taking to the right side of the point C? What was the value I have? Okay, two values we have calculated. Shear force minus 70 kilonewton. Shear force at B, it was 5.7 kilonewton. Shear force at C, okay, left of C, how much you got? Minus 34.3 kilo newton. Okay, right of C, right of C. So what will happen is one more load will add to this in downward direction. So it will be this whatever value we have calculated, which was minus 70 plus 75.7 minus 10 into 4 minus 40. Now this 40 kilonewton will come in our picture. So this will be minus 74.3. Is that correct? What you get? Okay, earlier when I asked to the left of C, this 40 kilonewton was not present over there in my shear force calculation. Okay, my section was somewhere over here. At this point, I have placed the section XX. Okay, and all the loads which are to the left side of section have been taken here. Minus 70 plus VP and due to ideal 10 into 4. Okay, minus 70 plus 75.7 minus 10 into 4. Okay, so now when I cross this point, okay, point C, and place my section to the right side of that concentrated load, okay, what will happen? Now one more force what will come in picture is this 40 kilonewton minus 40 kilonewton. Okay, so that will add to that one. So this will result in a UDL of minus 74.3. Now directly what we'll do, we'll go to point D here now. Okay, so shear force at D, right? So I'll calculate to the left of D, left of D. So what will happen? All the loads which are there to the right side of section, I'm placing my section over here to the left side of D. So what are the loads here? Minus 70, okay, plus BB, which is 75.7 5.7. Okay, due to VDL minus 10 into 7 meters. Okay, this is 4 plus 3, 7 meter. Okay, minus 40 concentrated load at sea. Okay, so this will be the value minus 74.3 still. Okay, sorry, it will have, I think it will change because this is now 7 meters. What is the value? Sorry. So this value will change.
104.3 minus
Okay,
104.3.
minus 104.3 minus 104.3, right? So it is coming out to be same as VD. Okay, so at the supports, this is what you get, like this end supports. Okay, they'll be equal to VD. Okay, when I cross this height of T, shear force will be 0. You can check that. When you cross this, what will happen? One force which is acting in upward direction. So minus 104.3 will be there. To this, what we'll be adding is this VD reaction, which is left side upward force positive. So I have to add this plus 104.3. So it will become 0 over there. Okay. So this is these are the values of shear force over here. Right. Now what we require is the bending moment values. Okay. So what will be the bending moment values in that case? So this is our beam, what I have taken. Okay. So okay, we'll go with this calculation from here. Okay. So what are the bending moment values? Again, we'll move from this end A itself. So bending moment over here at A. So we have a clockwise couple over here. Okay, directly at A, there is a clockwise couple. So as per sign convention, what you have, left side clockwise movement positive. Okay, that will result in sagging bending moment. Okay, so left side clockwise, this is the positive sign convention for our bending moment. So here it will be plus 100 kilonewton meter. Okay, and go to point B, bending moment at B. Okay, now what is the value of bending moment at B? Now we'll take moment due to all the forces which are to the left side of this section. Okay, so I have already this couple of 100 kilonewton meter. Okay, 100 kilonewton meter, and due to the concentrated load of 70 kilonewton, what will be the moment? Now this load will have an anti-clockwise moment about point V. So it will be minus 70 into 2 meters. Okay, because this will result in left side anti-clockwise moment, which will be negative. So that will be minus 70 into 2. So what will be this equal to? This is 140. So this will come out to be minus 40 kilo Newton meter. Okay, this is our moment at B, bending moment at B. Okay, so after this, what we'll do? We'll go to point C here now. Bending moment at C. Okay. Now here, since a couple is there, we'll see that when you have couple present over here, like our shear force, there will be a sudden change in the bending moment when you cross this couple and before crossing the couple. Okay. And we'll take first left of point C, to the left of point C. What is the bending moment value? So we have 100 kilonewton meter couple, this one clockwise, left side clockwise positive, minus 70 into, what is the distance now? 2 plus 4, 6 meters. Okay. I'm taking moment about point C. So 70 into 6 meter. Okay. And plus due to VB, movement will be clockwise, left side clockwise movement, positive, plus what was the value of VB? 75.7. Okay. Into what distance? 4 meter distance. Into 4 meter distance. Okay. So UDL, what is the moment due to UDL? It will be anti-clockwise. Okay, it will be having an anti-clockwise movement about point C. This is in downward direction, so it will produce an anti-clockwise movement about point C. Minus 10 into length of UDL 4 meter into 4 by 2, 4 meter by 2. Okay, so this will be the total movement about point C just before I cross that couple which is applied at point C. So what this comes out to be totally, if you calculate this total, what will be the answer?
-97.2
Minus 97.2 kilonewton meter. Okay. Now, when I cross that concentrated, sorry, not concentrated load, and I cross this couple, when I take that couple into my consideration, when I cross this point C, when I'm to the right of C, what will happen? Here, I have not considered this 150 kilonewton meter couple here. Okay. When I consider, there will be a sudden change here now. What will happen to the value? So this will be the bending moment up to point C, which will remain same, this equation. So plus 75.7 due to all other loads which are present to the left of the section. So it will be same, minus 10 into 4 meter into 4 meter by 2. Okay. So 4 meter by 2. Okay. Plus this 150 kilonewton meter. Now that will be taken here. Okay. So at the same point itself, it is changing suddenly. Okay. So what will happen? So this was entirely, this was coming out to be minus 97.2 plus 150. Minus 97.2 plus 150. How much that value will come out to be?
52.8.
52.8 kilonewton meter. Okay, so at point C itself, we are having two values of bending moment which are changing suddenly, minus 97.2 and plus 52.8, right? So at point D, the bending moment will be 0. I can directly write that bending moment at D will become 0 because this is a hinge support here. Okay, what is provided. So at a point of hinge support, movement is 0. Okay, movement has to become 0 at such support. Here it will not be 0 because this is not an end support. It is not provided at the end of the beam. So here the movement will not be 0 at this point support B. At support D, which are the end hinge support in the beam, there the movement will be 0 here. So directly I can write bending moment at point D is equal to 0. This will also serve as a check for you. Okay, if you can go and calculate and see that at D it will turn out to be 0. Okay, so you can start taking sum of all the moments to the left of section at about point D and you should get that to be 0. Okay, so somewhere between these, at this point here, there is a change in the bending moment. Okay, sudden change in the bending. It is changing from negative to positive here. We can note this. Here the value is negative and it is turning out to be positive suddenly. Okay, somewhere in between it is also becoming 0 there. Okay, so that point, okay, these. Okay, just see here at point C what I'm getting minus 97.2, and once I consider this couple, it is changing to plus 52.8. So from negative to positive, bending moment is changing from negative to positive. So somewhere in at this point C itself, it is also becoming zero. Okay, so that point where the bending moment is changing the sign, that point we call it as point of contraflexion. So for me, my point of contraflexion is at point C itself. Okay, at point C only, the bending moment is changing from negative to positive. Somewhere over here, at point C, we have a point of contraflexion over here. Okay, we'll plot this in the next class. Okay, just go through these calculations and try plotting on your own. We'll continue with this problem code, plotting of this bending moment and shear force. Try plotting the bending moment and shear force, considering the previous example. Okay. Right, we'll finish if you are given the attendance. If not, put your attendance in the chat box. USN. And any doubts, any difficulties in this module or other modules, please tell me. We can have a repetition. Exactly once you are given the attendance.